But what if you have this giant complex and you're trying to solve for capacity? You want to maximize return on investment for different capacities of all sorts of different units. This is one of the reasons, one of the challenges, we ended up creating our own tools. To optimize capacity at a unit level requires not only linear programming, but RAM study information, whether the units are available or not, and a dynamic flow solver. So what we've created is a dynamic flow-solving linear program that moves through time and does all the same things as a RAM study, optimizes for flow like a linear program, and has dynamic mass balances, much less like a dynamic simulation, but it's a dynamic flow solver like in a dynamic simulation. We call it COST, our capacity optimization and sizing tool. It takes those three together. Clients needed this information. They needed to know, how big should this tank be? How big should this unit be? Yes, we know we want a 100,000 barrel a day something there, but should it be 105? Should it be 95? What should it be? And with this kind of tool, we are now able to come in and say, well, this tool allows us to empirically, using numbers, come in and say, this is the solution. This, again, is the same basic question. How will changes in capacity affect production and therefore affect revenue? So how big is the carrot in making this change? But the problem is that often a pro forma, the business plan for whatever this is, makes some sort of assumption on production. It says, well, tribal knowledge, we've seen this kind of thing. It's general practice that yeah, this is kind of what we should expect here, with no real analysis done to see if that's really true. Or some expert someplace says, yeah, I've seen that there, so we're going to see that here too. And that's really prevalent. It's mostly because there haven't been real analytical ways to do this kind of thing in the past. We're trying to get past that. We had a client that had that, what we showed you was an upgrader. How does additional upstream capacity and tank infrastructure affect revenue? How do improvements, do those improvements, are they justified by improvements in ROI? Which capacities generate the highest ROI? And especially tanks, we get the biggest interest on sizing tanks. How big should a tank be? For a quick example of this, so if you had a distillation unit, that the bottoms went to a de-asphalt, which is that upgrader, and you had a tank here, and you had gasifiers producing hydrogen to go to this hydrocracker. This is a split flow system. What if we put a new tank in here? How big should that tank be? What is the value of that tank? Or what if we put in a hydrogen plant here to supplement hydrogen, because I've yet to meet a reliable gasifier. What if we put in a new hydrogen plant here to supplement hydrogen? What if we did both? Well, from a traditional reliability block diagram point of view, it would have looked something like this, where we have distillation, de-asphalting, and all these things are allowing us to fill this tank. We can't fill this tank unless all these things are running, and we have this hydrocracker basically drawing down from it. Well, adding the hydrogen plant would be a relatively easy exercise, but where would you put this new asphaltene tank? It doesn't fit this structure, and getting to a failure logic that fits these complex structures is often erroneous. It's very easy to come up with a scheme here that seems to make sense in many cases, but in many cases does not. So why translate it from that into that when you can just model that? That's really what we ended up, that was the challenge we needed to solve. And that's now what we can do is we can apply failure data to these things and say, what is our production? So for this whole system, all these things that are different colors, we looked at all those different tanks. How big should those tanks be? How big should units be? Etc. This is what you should be looking for. How much improvement do we have if this particular tank here, if we went up to 50% of the design capacity, we get a pretty good return. We only get another 1/10 of a percent. It's a good reason to build that first tank, but not that second tank. Yes, it improves from here to here, but if it's a $30 million tank or whatever it is to put in that tank, is that worth that extra 1/10 of a percent? Sometimes it is. Sometimes a 1/10 of a percent in refinery is a lot of money, but often it is not. Where in here We give that, what are the best financials in this? If we do the full capacity, there is a good reason to build just even a small hydrogen plant, but getting up to a much bigger, it still gains for building a bigger hydrogen plant, but not necessarily enough to justify the expenditure. This kind of analysis can be done when we combine all those things together.